Assalamu alaikum everyone. This is the accompanying video for project 2 of EE100 and the name of the project is Estimating Rain. So what you see right now on the screen is an image of Namal Valley, in fact a satellite view, and what you see in marked by the stars are rain gauges that we have placed in the valley, and these rain gauges give us measurements of rain at the location where we have installed these rain gauges. Now, the rainfall maps that you would have seen on the news are actually of the sort of what you see on the right hand side. Now, on the right hand side, you can see that it's a plot where on every point, every long lat, you have a reported measurement for rainfall. Now, you can see that the locations of the sensors have been overlain on this plot. You can see them in red. And the thing that I want to emphasize over here is that even though the rainfall measurements are being obtained only on these red stars, the precipitation map has a reading for every long lat. And this is what this project is going to be about. So how to go from the figure on the left hand side to the plot on the right hand side. So what given how that I know what the reported measurements of the rain gauges are, what can I say about the measurement at another location where there is no sensor? Now, a way of thinking about this is that we have this underlying process that we want to observe. This does not have to be rainfall, although in our case this is rainfall, but this can be anything. And we want to observe this process or estimate this process at all locations, given only the readings from sensors that are located at specific locations. And another view for this is that you have these sensors at x1, x2, x3, these locations, and you want to say something about the measurement at this other point x naught. All right, so this is the fundamental problem that this is going to be about. Now, while we're only concerned with rainfall, the problem is very generic and applicable in a lot of other settings. So, for instance, here is a network of tube wells, Vasa tube wells installed in Lahore. Now, the tube from the tube wells, you can actually get information of the water pumping on exactly where the Vasa tube wells are located, but there is pumping going on everywhere else. But if you want to estimate the groundwater table depth or some other parameter, the same sort of methods would apply for that we are going to see in this project for rainfall. And on the screen right now, what you see is a map for dengue probabilities in Peshawar. Now you can see that the probabilities have been calculated at every point of the map, but we only have observations where there are red crosses that are shown. All right, so the same sort of problem we deal with over here. Now on this, in this figure, you have this map of arsenic levels in water, groundwater in Punjab and Sindh. And you can see that the measurements have been taken at these points that have been plotted here, but the arsenic levels have been shown for all of the points. In fact, it's like a continuous contour map. All right, so these are all examples of what we want to do for rainfall that is also applicable in other settings as well. Now, in order to start building an understanding of how we're going to solve this problem, let's look at a simplified example. So imagine that you have this piece of land and you want to estimate something that varies with the location of the land. Now, this could be the level of the water table. It could be the level of contamination in water. It could be air pollution. It could be air temperature. It could be rainfall. It could be anything. But essentially what you have are these four sensors that are placed at locations x1, x2, x3, and x4. And you have this point x naught, and you want the measurement at x naught but you have no sensor over there. You have sensors at x1, x2, x3, and x4. So essentially the question is this. So given the measurements, which we call z, which is a function of the location. So given the values of the function of the quantity at x1, x2, x3, x4, can we find the quantity at x naught? And the way that we do this mathematically is that we combine all of the available measurements by adding them together after multiplying them with certain weights. So in this equation, you see that the estimate of the quantity at x naught is actually a number lambda1 multiplied by zx1 plus a number lambda2 multiplied by zx2 and so on. All right, and we call these lambdas as weights. So essentially what we've done is we've translated our problem into the calculation of these weights. All right, so if someone gives me these weights, then I will be able to find the measurement at the other point x naught. All right, so this is what this is um, going to be about. So let's see how we can find these weights. Now at the backbone of this weight calculation is going to be this thing called a variation. Now the variation is very simple to understand. It's just exactly what the name implies. It's the difference or a measure of difference between two quantities. All right. Um, So if I want to see the variation between the measurement reported at two values, I just take the difference and square it, right? So this difference actually depends on the distance between the sensors. All right, so I can say with some confidence that the further away I am from the sensor X1, all right, so you consider only a single sensor here for simplification, and the further away I am from that sensor, the more variation I can expect. All right, so if I have a rain gauge at LUMS, and I want to say something about the rain at Walton, so I can expect something different from LUMS, all right? And when I go to Gulbarg, that is even further away from LUMS, all right? So the difference in rainfall from LUMS will be greater in Gulbarg as compared to Walton because Gulbarg is further away from LUMS. So this distance we represent by this variable h, and you can see in red underneath in the slide here that this is actually the Euclidean distance. This is the same notation that has been used in your project handout. It's simply the sum of squared differences between the x coordinate and the y coordinate. Now the intuition is that larger h results in larger variations. Now if you can actually actually estimate how variations actually occur as a function of distance, then you've actually got all that you need in order to construct those weights. So this is actually encoded in something called the variogram. And this is the representation of the variogram. So on the x-axis you see the distance h, and on the y-axis you see the so it's the variogram basically, but you can understand it as the average expected variation, right? So you can see that the more you move on the h-axis, the x-axis, the more variation you get. It is rising and it also settles down somewhere eventually. So it means that after a particular distance, it doesn't matter how much further you go. All right, so the variation is going to be the same. So it's like saying that that the correlation of rainfall between Lahore and Hyderabad is the same as the variation in rainfall between Lahore and Karachi, even though Karachi is further away from Lahore than Hyderabad, so to speak. All right. So and it's of course it starts from zero because there is no variation if you put two sensors at the same location. All right, so that's the assumption here. So what we're going to do is that we're going to record these average variations between the sensor values, the history of the sensor values, and we're going to basically be recording the variation and plot them against the H values. All right. So as I said, the calculation of H is pretty straightforward. If you have x1 as this vector 3, 4 and x2 as this vector 6, 8, then H is simply 5. And for our particular sensor network in NUML, we have 7 rain gauges, and these coordinates will be given to you in the lab handout. So what you're essentially going to do is that you're going to observe variations between pairs, log them, and plot them against H. Now there are 7 sensors, so 7 choose 2. You have 21 pairs of sensors, so you have 21 pairs of the variation and distance. And this is the complete data that is given to you. So the on in the first column you have the dates. All right, so these are the rainy days of the monsoon season for this year, and the columns have been named according to the sensors where they have been placed. We have a sensor at Kalri, at Dhokund, at Dhokpira. These are all names of local villages in the valley. And so what you will essentially be doing, so you pick any date, so for instance 11 June. Now you have 7 sensors reporting their values on 11 June, and you can observe the variation between Kalri and Dhokund, between Kalri Dhokpira, between Kalri Kund House, and so on. All right, so then you pick the second sensor between Dhokund Dhokpira, Dhokund Kund House, Dhokund Namal Dam, and so on. All right, so you observe all of these, record all of these variations, and also note the value of H, the distance. And if you plot them against each other, you get these red dots that you see on the screen. And um, once you plot these red dots, you get this what we call experimental variogram. So I'm sorry, you get the raw variogram, and you have been given a piece of code. So once you have this this raw variogram, then you just run the piece of code. You actually fit a line between this. All right, and this is going to be your theoretical variogram. All right, so we want to fit this line because when we're calculating the weights for estimating rainfall at some point, you will be using the values of the variogram at any other point which whose distance was not included in the sensor network. All right, so agar aapke paas, so now that you have this blue line, if you want to take the variogram at, for instance, 17 distance. Now, there was no such pair at 17 distance in the sensor network, but because you now have this theoretical variogram, you know that all right, at 17 you have like a variation of 200 or something. So this is going to be your deliverable for the first week of this project. So now that you have this variogram, the next task is going to be actually estimating the rainfall at some unobserved point. So as I said before, you have these lambdas and you want to reconstruct these lambdas. And the way that you're going to do it is actually a very neat and simple algorithm. It's called Krigging. And Krigging essentially sets up a system of equations. All right. So what you do essentially is that you stack up all of the weights, lambda 1, lambda 2, up to lambda n, into this vector x. And at the end, there is this other parameter nu. For now, we can consider this as an intermediate variable. And I expect that in the next semester or the next one, when you take more advanced mathematics courses, you'll actually You'll actually get to know a name for this parameter new, but for now it's just an intermediate parameter. So if you find this vector x, then you're done. All right, so you get all the weights lambda 1, lambda 2 till lambda n, and then you get this set of equations. All right, so this we call the Krigging system. Now this Krigging system is simply ax is equal to b. Now in the project, in the project handouts, you've actually been told how to set up these matrices A and B. So let me just show you what these matrices are. So these are the matrices. Now you can see that in for matrix A, there are just the values of the variogram. All right, so so for instance, the entry in the second row and the first column is gamma of whatever the distance between sensor 2 and 1 is. All right, and as you go down, you get you get to the variation between sensor 1 and n. All right, so this is how you're going to set up these matrices. You will have to set up these matrices in the next task, in the lab handout as well, and just observe that all of the variations in A are between the points where the sensors are installed. All right, whereas the vector B includes the variation between of the um, all of the sensor locations between the unknown point. All right, so you can pre-compute A, and whatever point you want to get the estimate for, you construct the B vector for that point only. So now, once you've set up the Krigging system, you can simply do x equals A inverse B, and you will get the weights lambda, and then you do the estimate by just multiplying the individual lambdas with the individual sensor measurements, and then you get the expected value, the estimated value of the rainfall. Now, an additional quantity that the Krigging system gives to you is called the expected error. All right, so you can say, all right, so I expect at x naught, the value is going to be like 100 mm plus minus, I don't know, 10 mm or something. All right, so that's the expected error, and you also have a way of calculating this expected error as well. So as we're going to see in the next task, this is going to be a very useful quantity for us. So now you know how you have to go from the left figure to the right figure. All right. So for every point, you set up a Krigging system, you invert it, you find the weights, and you multiply all the sensor values for those weights, and you get the estimated rain. At that point, you can form these Krigging predictions, this rainfall map. All right. So there is a unique set of weights for every separate point. All right, so for each point for each lat long, you get a separate set of weights, and you can reconstruct the measurements from those weights. Now, your last task is actually an open-ended task. There's not much hand-holding there. We've given you a template for the code of the previous task, and this is going to be where you would have to think a little. So assume that we have an 8 sensor, all right, and we want to figure out where is a good location to put it. All right, and in your handout, you've been given two candidate locations, so you can either place it at location 1 or location 2, and you're going to tell where that additional sensor should be placed. Now, one very good criterion that is actually followed in practice is the expected error. All right, so remember that in order to calculate the weights, we don't actually need the measurements. All right, so we only need the variogram. All right, so your matrices A and B, they only require the variogram. All right, so you set up a Krigging system for both of the locations, and you can get the expected error for for uh, for that location exactly. All right, so your task will be to calculate the expected error at both of the candidate locations, and wherever the expected error is less, you recommend to place the sensor over there. All right, so this is your last task. Now, I hope that when you go and look at the handout, you will be able to read it and understand it on your own. All right, so good luck. And if there are any questions, you can ask the TAs, or you can ask me in person as well. I will be available on campus. And yeah, so I look forward to your submissions and seeing what fun sort of projects you come up with. Assalamu alaikum and Allah Hafiz.